Welcome. In this lecture, we're going to talk about the work done by a non-constant force. And we've already talked about the work done by a constant force, and we've talked about the fact that the force exerted by a spring is a non-constant force. It's linear, and it's given by Hooke's law. The force of a spring is equal to negative kx. So now let's talk about the work done. And to get there, let's first talk about the work done by a constant force, but let's graph it. So on the vertical axis, we've got F. And on the horizontal axis, we have x. And if it's a constant force, then it's represented by a horizontal line. And if we want to know the work done from some position x equals 0, let's say, to some position out here at x1, then we know that the work equation is the work is equal to force dotted with dx. And we know that's F, the magnitude of the force, times the displacement, times the cosine of the angle between them. Let's say, for argument's sake, that the force here is in the same direction as delta x, and so the cosine of phi is going to be 1. So we're just looking at the work is equal to force times delta x. We'll take a look at what that is. The horizontal, let's say if this is a big rectangle right here, then the length of the rectangle, delta x. That's that entire side of the rectangle. And the height of the rectangle here is just F. So we are multiplying F times the displacement, force times displacement, and we get the area under our force versus displacement curve is equal to the work. So area under F versus x curve equals the work. So let's take that to a situation where we have a non-constant force acting. Again, we're going to graph force on the vertical axis, and we're going to graph displacement or position on the horizontal axis. And let's say that for the first amount of time, we're doing a force F1, and then we get tired, and the force that we apply is less. That'd be F2 maybe, and then we get told by our boss to hurry up, and so we apply a greater force this time. So we've got F1, F2, and F3. So this is a changing force, and it doesn't change instantaneously, but it changes pretty quickly. So we want to know the total work done in this entire displacement and moving this object from some position 0 all the way out here to position x. And again, as we saw before, it's just the area under the curve. So this is really easy to find the area between these curves because we have 3 rectangles. And we would do F1 times this first displacement, x1 minus 0. And then we go here and do F2 times this displacement, which is x2 minus x1. That'll give us the area of that rectangle. And then finally, we would do F3 times this displacement here, x minus x2, and that gives us the area of that rectangle. So again, the area under the curve is going to be the work done. All right? So let's take a look at what this looks like for a spring, an ideal spring. So this is work done by an ideal spring. And remember that when we say ideal spring, we're talking about a spring that conforms to Hooke's law. The force applied by the spring is equal to negative kx. The force and the displacement are in opposite directions. Let's take a look at a specific situation here. Let's say we've got a spring attached to a wall, and we've compressed the spring, and we've put a mass m on the end of this spring. It's sitting on a frictionless surface, and we have compressed the spring by some delta x here from its rest position. And we're going to let this mass go. And we know that as we let the mass go, the spring is going to apply a force on the mass to the right. And as that mass moves to the right, accelerates to the right, the force applied by the spring gets less and less and less because that delta x gets smaller and smaller and smaller. And we know that the force applied by the spring is equal to that negative kx. So if we graphed this, the force versus the position of the spring, the force starts out at its maximum because it's displaced its largest amount. And then as the displacement gets smaller and smaller and smaller, wait Let me think about that for a second. Correction, the force doesn't start out here. The force starts out here at its maximum. So for the biggest displacement, delta x, you're going to get the biggest amount of force. So that is this situation right up here. The block is at rest. We're ready to let it go. Now, as the displacement gets smaller and smaller and smaller, as the spring moves back towards its rest position, eventually, when the spring gets at its rest position, the force is going to be 0, and so is x, the displacement. So now we've got this situation right here. And that should look familiar from class the other day when we did our lab stretching the spring. We get a nice little linear force versus position graph. Now, what we found before was that the area under the force versus position graph is going to give us the work done. So if I want the work done by the spring, I'm looking at the area of that triangle now. So the bottom of the triangle, the base of the triangle, is our delta x. And the very top of the triangle, the height, is this f at whatever that position x was, the maximum displacement. All right, so if I want to know the work done, it's going to be the area of this triangle. So area of a triangle is half the base times the height. So half the base is half of delta x times the height here, which is the force, that maximum force at the position x. But we know from Hooke's law that F is equal to kx. So the work done here is going to be half of, let's just, instead of saying delta x, we'll just say x. Half of x times that F, which is kx. All right, the force on the spring is positive here, so I'm going to make my kx positive. And so then we get the work done by the spring, 1/2 kx squared. And this is a general equation that holds for any ideal spring, any spring that conforms to Hooke's law. The work done by the spring is 1/2 kx squared. Very worth remembering, and I'm pretty darn sure it's on your equation sheet as well, but we can double check that. Okay, so let's look at an example here, and it's the same example we just looked at. We've got a spring that's compressed, and it is going to accelerate this block all the way to this position x1. And then the block's going to get released, and it's going to cruise. And we want to know what is the velocity of the block right here when the spring is done pushing it. All right? So we can use the work-energy theorem to answer this question, because we remember that the net work done on an object is equal to the change in kinetic energy. And this is going to allow us to relate the force that the spring applies over the distance to the change in the kinetic energy, which is going to allow us to relate it to velocity. We could not have answered this question using Newton's laws and kinematic equations, because the acceleration of the block while the spring is pushing it is not constant. Quick free body diagram for the block. We've got this applied force, which is the spring force. We've also got mg going down. We've got the normal force going up. There is no friction between the block and the surface. So it's easy to see here the weight doesn't do any work because it's at a right angle to the displacement. The normal force doesn't do any work because it's at a right angle to the displacement. So the only thing that does work is the spring force. So we can say that the work done by the spring in this case is going to equal the change in the kinetic energy, K final minus K initial. And let's see here, K initial, it starts at rest, so this guy right here is 0. That simplifies our equation dramatically. So the work done by the spring we already learned in the previous one is 1/2 kx squared. And I'm going to say be careful with the work done by the spring. It can be positive or it can be negative. You have to think about the situation and judiciously put in a plus or a minus here in front of the work done by the spring. Just look at the situation. Is the spring's force speeding the object up? Great, the work is positive. Is the spring's force slowing the object down? Great, the work is negative. We could easily imagine a reverse situation where we've got a block out here and it's coming at the spring with a certain velocity, hits the spring and compresses the spring. In that case, the spring is acting to slow it down. We get a negative. All right, we cannot just look at the x, the delta x, to give us positive or negative because it's squared in the equation. All right, so we have to judiciously determine if the work done by the spring is positive or negative. In this case, it is positive because it's speeding up the block. And this is going to equal 1/2 mv final squared. Notice mass does not cancel out when we're dealing with spring problems because I don't have an m on the left-hand side. We are looking for v final squared. The halves do cancel. Dividing by m and taking the square root, we have k x squared over m. We take the square root of that. That is equal to v final. If you wanted to clean it up a little bit, you could say x times the square root of k over m, because that x squared comes out from under the radical, and that's equal to v final. But that's the basic situation right there. So with this setup, keep in mind that we could solve for k if we had the opposite situation where the velocity was coming in, the block was coming in and hitting the spring and compressing it. We could solve for k, we could solve for x, we could solve for the mass of the block even. All right? So this is the kind of stuff that you're going to be doing, using the work-energy theorem, this guy right here, to solve problems involving springs pushing things, springs slowing things down. Always remember that the area underneath our force and displacement graph is going to give us our work. All right? So again, area equals work. Oh, one last thing. I should have said this as well. If we've got a graph of force versus position here, and our graph does this, remember that area above the axis is going to be positive work. Area below the axis gives us negative work. And to find the total work done over that entire displacement, we would have to add in the negative work and the positive work together to get the total work done. All right, so keep that in mind as well. All right, see you next time. Thanks.